For as long as humans have looked to the heavens, we've sought stories in the stars, guides for our travels and inspirations for our myths. In this documentary, we embark on a journey into the world of pulsars, rapidly spinning stellar remnants that pulse with astonishing precision, offering us profound clues about the universe's most secretive corners. You will discover how a curious graduate student's chance of finding sparked an entire branch of astronomy, how these cosmic lighthouses help us test Einstein's theory of gravity, and why their near-perfect regularity could one day reveal elusive gravitational waves.
We'll visit the world's most advanced radio observatories, both on Earth and in space, tracking signals that travel from thousands of light years away. You'll learn how these beams of radiation illuminate the life cycles of stars, shed light on the ultra-dense matter inside neutron stars, and push the boundaries of what we know about energy, magnetism, and even time itself.
Along the way, we'll know the pioneers who first detected that mysterious blip among cosmic static, walk through the awe-inspiring breakthroughs that followed, and catch a glimpse of the future telescopes poised to uncover a hidden symphony of spacetime.
By the end of this journey, you'll see pulsars not just as distant curiosities, but as vital keys to understanding our cosmic origins, the nature of matter at its most extreme, and the silent, ongoing dance of galaxies across eons.
So join us as we shine a spotlight on these spinning stars, the precise pulsing signals that continue to transform our view of the universe and promise new discoveries for generations to come. The story of pulsars is intertwined with the story of radio astronomy, a relatively new branch of science that emerged in the 20th century. Radio telescopes, unlike their optical counterparts, don't detect visible light. Instead, they capture radio waves, a form of electromagnetic radiation invisible to our eyes. In the 1960s, radio astronomy was still in its infancy.
Astronomers were just beginning to explore the universe at radio wavelengths, making surprising discoveries. It was against this backdrop of discovery that a young graduate student named Jocelyn Bell Burnell made a finding that would change astronomy forever.
While working with her advisor, Anthony Hewish, at the Mullard Radio Astronomy Observatory in Cambridge, England, Bell Burnell noticed something peculiar in the data from a newly constructed radio telescope. There, amidst the cosmic static, was a regular signal, a pulse of radio waves repeating every 1.3 seconds with astonishing precision.
At first, Bell Burnell and Hewish thought it might be interference from a terrestrial source, or perhaps even a signal from an alien civilization.
Bell Burnell's discovery, initially met with a mixture of excitement and skepticism, sent shockwaves through the scientific community. The idea of a celestial object emitting such regular pulses of radio waves was unprecedented. Theorists scrambled to explain the phenomenon, proposing a range of possibilities, from pulsating white dwarf stars to exotic new forms of matter.
But as more pulsars were discovered, a consensus began to emerge. The signals, it seemed, were coming from rapidly rotating neutron stars,
the remnants of massive stars that had exploded as supernova. The discovery of pulsars was a watershed moment in astronomy. It confirmed the existence of neutron stars, objects so extreme that they had previously been relegated to the realm of theoretical speculation.
It provided a new tool for studying the properties of matter under extreme conditions that could never be replicated in a laboratory on Earth.
And it opened up new avenues of research,
from the study of gravitational waves to the search for extraterrestrial intelligence.
To understand how pulsars work, imagine a lighthouse standing on a distant shore.
As the lighthouse rotates, its beam of light sweeps across the sea, appearing as a flash of light to an observer on a ship.
Pulsars operate in a similar way, but instead of beams of light, they emit beams of radio waves, as well as other forms of electromagnetic radiation, such as X-rays and gamma rays. As a neutron star spins, its powerful magnetic field channels charged particles along its magnetic poles. These charged particles, accelerated to nearly the speed of light, emit radiation in a narrow beam that sweeps across space like the beam of a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation each time the beam sweeps past us. The regularity of these pulses is astonishing, rivaling the precision of atomic clocks. Pulsars, these cosmic lighthouses, have become invaluable tools for astronomers, providing insights into a wide range of astrophysical phenomena.
By studying the properties of pulsar signals, scientists can probe the extreme environments around neutron stars, study the interstellar medium, and test fundamental theories of physics.
One of the most exciting areas of pulsar research is the search for gravitational waves. These ripples in the fabric of spacetime, predicted by Einstein's theory of general relativity, are produced by some of the most violent events in the universe, such as the collision of black holes,
or the explosion of supernovae. Pulsar timing arrays, networks of precisely timed pulsars spread across the galaxy, are being used to detect the subtle stretching and squeezing of spacetime caused by gravitational waves.
These arrays are essentially giant gravitational wave detectors, capable of sensing ripples in spacetime from sources billions of light-years away. As we delve deeper into the study of pulsars, these cosmic beacons promise to illuminate not only the mysteries of distant stars, but also the fundamental nature of our universe. As weeks turned into months, Bell Burnell became intimately familiar with the patterns of radio noise that filled the charts.
She could distinguish between interference from terrestrial sources, like passing cars or distant radio broadcasts, and the faint hiss of the cosmos itself.
It was during one of these meticulous examinations, her eyes scanning the endless lines on the chart paper, that she noticed something utterly unexpected. A peculiar signal, a pulse of radio waves, stood out from the background noise. It was faint but distinct, repeating at regular intervals. At first, Bell Burnell dismissed it as a possible anomaly, a glitch in the telescope's instruments or a stray signal from a nearby source. But the signal persisted, appearing night after night, its regularity too precise to ignore. Intrigued and puzzled, she consulted with her advisor, Anthony Hewish, a renowned radio astronomer. As Bell Burnell and Hewish continued to observe the mysterious signal, its characteristics became increasingly perplexing.
The pulses were incredibly regular, repeating every 1.3 seconds with an accuracy that rivaled the best atomic clocks on Earth.
Such precision seemed almost artificial, leading to some playful speculation among the team.
Half-jokingly, they dubbed the source LGM-1, short for Little Green Men 1.
Could this be a sign of an extraterrestrial civilization, its signals beaming across the vastness of space?
While the idea of alien contact captured the imagination, Bell Burnell and Hewish remained grounded in scientific rigor.
They meticulously ruled out all other possible explanations, from terrestrial interference to instrumental malfunctions. The turning point came when Bell Burnell discovered a second pulsating source, this one with a slightly different period, ruling out the possibility of a single, localized phenomenon.
It was becoming increasingly clear that they were dealing with a new class of celestial objects, something entirely unprecedented. The scientific community was abuzz with excitement and speculation.
Theorists proposed a range of explanations, from pulsating white dwarf stars to rapidly rotating neutron stars, exotic objects predicted by physics but never directly observed. The neutron star hypothesis, initially met with skepticism, gradually gained traction as more pulsars were discovered. The term pulsar, short for pulsating radio star, was coined, capturing the essence of these enigmatic objects. Among the early pulsar discoveries, one stood out as particularly significant: the pulsar at the heart of the Crab Nebula.
This expanding cloud of gas and dust, the remnant of a supernova explosion witnessed by Chinese astronomers in the year 1054, provided a crucial clue to the nature of pulsars.
The Crab pulsar, as it came to be known, pulsed with a remarkably fast period of 30 times per second.
This rapid rotation, coupled with the nebula's known age, lent strong support to the idea that pulsars were indeed rapidly spinning neutron stars.
The discovery of the Crab pulsar cemented the connection between pulsars and supernovae, demonstrating that these extreme objects were not merely theoretical curiosities, but rather a fundamental part of stellar evolution.
It also provided a natural laboratory for studying the properties of matter under the most extreme conditions imaginable.
The discovery of pulsars, a testament to the power of human curiosity, and the ingenuity of scientific exploration, had profound implications for our understanding of the universe.
Jocelyn Bell Burnell's meticulous observations, initially met with skepticism from some quarters, earned her a permanent place in the annals of science. While the 1974 Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle for their contributions to radio astronomy, Bell Burnell's pivotal role in the discovery of pulsars has been widely acknowledged and celebrated.
The discovery of pulsars opened up new avenues of research, from the study of gravitational waves to the search for extraterrestrial intelligence. These cosmic timekeepers with their precise pulses provided astronomers with invaluable tools for probing the mysteries of the universe. And so, from a quiet observatory in the English countryside, a revolution in astronomy was sparked, forever changing our view of the cosmos and our place within it. To comprehend the awe-inspiring nature of pulsars, we must first journey into the heart of a dying star.
To the birth of a neutron star.
These stellar remnants, forged in the crucible of supernova explosions, are among the most extreme objects in the known universe, pushing the boundaries of physics and challenging our very understanding of matter itself.
Imagine a star far more massive than our sun.
Its core a raging inferno of nuclear fusion, fusing hydrogen into helium and heavier elements,
releasing unimaginable amounts of energy that counteract the relentless inward pull of gravity.
For millions or even billions of years, this delicate balance persists.
The star shining brightly as it converts matter into energy.
But eventually, the star's nuclear fuel begins to dwindle.
The outward pressure from fusion weakens, and gravity, ever patient, begins to gain the upper hand. The star's core contracts.
Temperatures and pressures soar to unimaginable levels.
And the stage is set for a cataclysmic event.
At the heart of this cosmic maelstrom, something extraordinary emerges from the ashes, a neutron star.
This stellar remnant, a sphere no larger than a city but containing the mass of our sun or more, is a testament to the incredible power of gravity, a force capable of crushing matter into states that defy our everyday experience.
The density of a neutron star is almost incomprehensible.
Imagine squeezing all the people on Earth into a single grain of sand.
That's the kind of density we're talking about.
In this extreme environment, atoms themselves are crushed, their constituent protons and electrons forced to combine into neutrons, hence the name neutron star.
The gravitational pull of a neutron star is equally mind-boggling.
If you were to stand on the surface of a neutron star, not that you could, as the gravity would crush you instantly, you would experience a gravitational force billions of times stronger than Earth's gravity.
Time itself would be warped in this extreme environment, slowing down significantly compared to time as we experience it.
Neutron stars are in many ways the ultimate cosmic laboratories, places where the fundamental laws of physics are pushed to their limits.
And it is from these extreme objects spinning like celestial beacons that pulsars, those cosmic lighthouses, draw their power. Imagine a giant bar magnet, its magnetic field lines stretching out into space, invisible but powerful.
Now, imagine that magnet spinning rapidly, its magnetic field lines whipping around like a cosmic lasso.
That's a simplified but evocative picture of a pulsar.
Neutron stars are born with incredibly strong magnetic fields, trillions of times stronger than Earth's magnetic field.
These magnetic fields are thought to be remnants of the original star's magnetic field, amplified to unimaginable levels during the core collapse that created the neutron star.
As a neutron star spins, its magnetic field rotates with it, creating an electric field that accelerates charged particles, such as electrons and protons, to nearly the speed of light.
These high-energy particles, spiraling along the magnetic field lines, emit radiation in a narrow beam that sweeps across space like the beam of a lighthouse.
If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation each time the beam sweeps past us.
The regularity of these pulses is astonishing, rivaling the precision of atomic clocks.
It's like a cosmic metronome ticking away with unwavering accuracy, a testament to the incredible stability of these spinning stellar remnants.
The discovery of pulsars revolutionized our understanding of stellar evolution.
Before pulsars, neutron stars were merely theoretical constructs, predictions of physics but never directly observed.
Pulsars provided the first concrete evidence that these extreme objects existed, confirming our models of stellar death and the processes that govern the life cycles of stars.
But pulsars are more than just curiosities. They are invaluable tools for astronomers, providing insights into a wide range of astrophysical phenomena.
By studying the properties of pulsar signals, scientists can probe the extreme environments around neutron stars, study the interstellar medium,
and test fundamental theories of physics.
One of the most important applications of pulsars is in the field of astrometry, the precise measurement of positions and movements of celestial objects.
Because pulsars are so incredibly regular, they can be used as celestial clocks. their pulses providing a reference point against which to measure the movements of other objects.
By carefully timing the arrival of pulses from pulsars, astronomers can detect the subtle gravitational tugs of planets orbiting other stars,
Map the distribution of matter in our galaxy,
and even test Einstein's theory of general relativity, which predicts that gravity can warp the fabric of spacetime. Not all pulsars spin alone in the vastness of space.
Some exist in binary systems, locked in a gravitational dance with a companion star.
These binary pulsars, as they are known, provide unique opportunities to study gravity, stellar evolution, and the properties of matter under extreme conditions.
One of the most famous binary pulsars is the Hulse-Taylor binary pulsar, discovered in 1974 by Russell Hulse and Joseph Taylor.
This system consists of two neutron stars orbiting each other, one of which is a pulsar.
By carefully timing the arrival of pulses from the pulsar, Hulse and Taylor were able to determine the masses of the two neutron stars and the characteristics of their orbit.
Their observations revealed something astonishing. The orbit of the binary pulsar was slowly decaying.
The two neutron stars spiraling closer together over time.
This orbital decay was exactly what Einstein's theory of general relativity predicted should happen if the binary system was losing energy by emitting gravitational waves.
The discovery of the Hulse-Taylor binary pulsar and the confirmation of its orbital decay provided the first indirect evidence for the existence of gravitational waves.
Ripples in the fabric of spacetime that had been predicted by Einstein decades earlier.
This groundbreaking discovery earned Hulse and Taylor the 1993 Nobel Prize in Physics and opened up a new window into the study of the universe.
Pulsars are renowned for their incredible regularity, their pulses ticking away with clockwork precision.
But occasionally, these cosmic timekeepers throw a curveball, exhibiting sudden changes in their rotation rates known as glitches.
These glitches, while relatively rare, provide tantalizing clues about the internal structure and dynamics of neutron stars.
The exact cause of glitches is still a matter of debate among scientists.
But the leading theory suggests that they are caused by interactions between the neutron star's superfluid core and its solid crust.
Imagine a spinning figure skater extending their arms.
As they do, their rotation slows down due to the conservation of angular momentum.
Similarly, when a neutron star's superfluid core, which is not coupled to the crust, suddenly transfers some of its angular momentum to the crust's rotation rate increases, resulting in a glitch.
By studying the frequency and magnitude of glitches, astronomers can learn about the properties of superfluid matter,
the coupling between a neutron star's core and crust,
and the evolution of these extreme objects over time.
Glitches, once thought to be mere anomalies, have become valuable probes into the hidden depths of neutron stars,
revealing the complex physics at play within these cosmic enigmas. The story of pulsars, like the celestial objects themselves, is one of constant evolution, a tale spun from the threads of scientific curiosity and technological advancement.
From the early days of charting pulses on paper to the sophisticated instruments of today, our ability to listen to these cosmic beacons has grown exponentially, opening new windows into the universe and pushing the boundaries of our understanding.
The late 20th and early 21st centuries have witnessed a renaissance in pulsar astronomy, driven by the development of increasingly sophisticated telescopes and data analysis techniques.
No longer confined to the radio spectrum, we now observe pulsars across the electromagnetic spectrum, from low-frequency radio waves to high-energy gamma rays, each wavelength revealing different aspects of these enigmatic objects.
Radio telescopes, the workhorses of pulsar astronomy, have grown in size and sensitivity, allowing us to detect fainter pulsars and study their properties in greater detail.
The Arecibo Observatory in Puerto Rico, with its massive dish stretching over 1,000 feet in diameter, played a pivotal role in many pulsar discoveries, including the first binary pulsar.
Tragically, Arecibo collapsed in 2020, but its legacy lives on, inspiring new generations of telescopes and astronomers.
The Green Bank Telescope in West Virginia, currently the world's largest fully steerable radio telescope, has taken up the mantle, its massive collecting area and advanced instrumentation, enabling it to probe the depths of space with unprecedented sensitivity.
And new arrays of radio telescopes, such as the Very Large Array in New Mexico and the Atacama Large Millimeter Sub-Millimeter Array in Chile are providing astronomers with sharper images and more detailed data than ever before. As impressive as these ground-based telescopes are,
the future of pulsar astronomy may lie in space.
Free from the distortions of Earth's atmosphere,
space-based telescopes can observe the universe across the entire electromagnetic spectrum,
providing a clearer view of pulsars and other celestial objects.
The Fermi Gamma Ray Space Telescope, launched in 2008,
has revolutionized our understanding of pulsars in the high-energy gamma-ray band.
Fermi's Large Area Telescope, with its wide field of view and sensitive detectors,
has detected hundreds of pulsars,
many of which were previously unknown,
and revealed the diversity of their gamma-ray emission.
NISA, the Neutron Star Interior Composition Explorer,
a NASA mission installed on the International Space Station in 2017,
is providing unprecedented insights into the interior structure and dynamics of neutron stars.
By precisely measuring the X-ray emissions from pulsars,
NISA is helping scientists unravel the mysteries of these extreme objects,
from the properties of their superfluid cores
to the nature of matter at the highest densities. Looking further ahead, the Square Kilometer Array,
an international collaboration to build the world's largest radio telescope,
promises to usher in a new era of pulsar astronomy.
With its vast collecting area and unprecedented sensitivity,
SCA will be able to detect thousands of new pulsars,
including those in distant galaxies,
and study their properties in exquisite detail,
opening up new avenues of research,
and potentially revolutionizing our understanding of the universe.
Among the most exciting prospects in pulsar astronomy is the potential to detect gravitational waves, those elusive ripples in the fabric of spacetime predicted by Einstein's theory of general relativity.
While the first direct detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, was a monumental achievement, LIGO and similar ground-based detectors are primarily sensitive to high-frequency gravitational waves produced by the mergers of stellar mass black holes and neutron stars.
Pulsar timing arrays, or PTAs on the other hand, offer a unique opportunity to detect low-frequency gravitational waves, which are thought to be produced by the slow spiral and merger of supermassive black holes at the centers of galaxies.
PTAs work by carefully monitoring the arrival times of pulses from an array of precisely timed pulsars distributed across the sky.
Just as a stone thrown into a pond creates ripples that spread outward, disturbing the surface of the water, gravitational waves passing through the galaxy should cause subtle variations in the arrival times of pulsar pulses.
By analyzing these variations, astronomers hope to detect the faint symphony of spacetime, revealing the mergers of supermassive black holes billions of years in the past, and providing insights into the evolution of galaxies and the early universe.
Several PTA collaborations around the world, including the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav,
the European Pulsar Timing Array, or EPTA,
and the Parkes Pulsar Timing Array, or PPTA, in Australia, are actively searching for these gravitational wave signals.
These collaborations, pooling their data and expertise, are pushing the limits of precision timing and data analysis, and they are on the verge of opening a new window into the universe, one that promises to reveal the hidden dance of supermassive black holes and the secrets of gravity itself.
Pulsars, with their extreme properties and predictable behavior, serve as cosmic laboratories,
providing unique opportunities to test the laws of physics under conditions that could never be replicated on Earth.
These celestial beacons allow us to study gravity, magnetism, and the nature of matter at densities far beyond anything we can create in a laboratory,
pushing the boundaries of our understanding and potentially revealing new physics. One area of active research is the study of the equation of state of ultra-dense matter,
which describes the relationship between the pressure, density, and temperature of matter at extreme densities,
such as those found inside neutron stars.
The equation of state governs the structure and stability of neutron stars,
and it holds clues to the fundamental nature of matter at the subatomic level. By measuring the masses and radii of neutron stars,
astronomers can constrain the equation of state and test different theoretical models.
This is no easy feat,
as it requires precise measurements of both the gravitational pull of the neutron star,
which can be determined from the orbital motion of a companion star in a binary system, and its size,
which can be inferred from its X-ray emissions. Another area where pulsars are providing valuable insights is in the study of fundamental physics,
such as tests of Einstein's theory of general relativity,
and the search for violations of Lorentz invariance,
a cornerstone of special relativity.
The extreme gravity of neutron stars provides a unique environment for testing these theories,
as any deviations from Einstein's predictions or Lorentz invariance should be amplified in such strong gravitational fields.
The interior of a neutron star remains one of the most enigmatic and challenging environments in the universe to study.
Crushed by the relentless force of gravity, matter inside a neutron star is squeezed to densities exceeding those found within atomic nuclei, forming a bizarre state of matter that we are only beginning to understand.
At these extreme densities, the familiar protons and neutrons that make up the atoms of our everyday world are thought to break down into their constituent quarks,
forming a sea of quarks and gluons, the particles that mediate the strong force which binds quarks together.
This quark-gluon plasma is thought to have existed in the first microseconds after the Big Bang, and studying it inside neutron stars could provide insights into the early universe.
Other exotic forms of matter, such as strange matter,
a hypothetical form of matter composed of strange quarks in addition to the usual up and down quarks,
or even more exotic particles predicted by extensions to the standard model of particle physics, might also lurk within neutron stars.
These possibilities, while still theoretical, highlight the potential of neutron stars as laboratories for exploring the fundamental building blocks of matter and the nature of reality itself.
As we continue to probe the depths of these cosmic enigmas, we can expect more surprises and discoveries.
Each new observation, each new theoretical breakthrough, brings us closer to unraveling the mysteries of extreme matter, the origin of the universe, and the fundamental laws that govern our cosmos. From their serendipitous discovery as enigmatic pulsating radio sources,
to their current status as invaluable tools for probing the universe, pulsars have captivated the imaginations of scientists and the public alike.
These celestial timekeepers, born from the explosive deaths of massive stars, continue to surprise and amaze us, revealing the intricate workings of the cosmos and challenging us to expand the boundaries of our knowledge.
As we enter a new era of pulsar astronomy, driven by technological advancements and a thirst for discovery,
we stand on the cusp of even greater revelations.
The next generation of telescopes, both on Earth and in space, will unveil fainter pulsars,
map their distribution across the cosmos with unprecedented detail,
and probe the extreme environments around these objects with greater precision than ever before.
Pulsar timing arrays, listening for the subtle symphony of spacetime, hold the promise of detecting the mergers of supermassive black holes billions of years in the past,
providing a glimpse into the early universe and the evolution of galaxies.
And the study of pulsars themselves, those cosmic laboratories of extreme physics,
will continue to push the boundaries of our understanding of gravity, magnetism, and the nature of matter itself.
The story of pulsars is far from over.
It is a story that began with a curious signal on a chart recorder,
and has evolved into a grand scientific endeavor, spanning continents, disciplines, and generations.
And as we continue to listen to the rhythmic pulses of these celestial beacons,
we can be sure that they will continue to illuminate the mysteries of the universe,
inspiring us with their elegance, precision, and sheer cosmic wonder for generations to come.
As we conclude our exploration of pulsars, these celestial lighthouses that have illuminated our understanding of the cosmos,
we are left with a profound sense of awe and wonder.
From their serendipitous discovery amidst the static of radio waves,
to their current role as precision instruments, probing the universe's most extreme environments,
pulsars have fundamentally changed our view of the cosmos and our place within it.
The story of pulsars is a testament to the power of human curiosity,
the ingenuity of scientific exploration,
and the enduring allure of the unknown.
It is a story that began with a simple question: what is that strange signal?
And has unfolded into a grand scientific adventure,
spanning decades, continents, and disciplines.
Jocelyn Bell Burnell's meticulous observations,
initially met with skepticism from some quarters,
ultimately revealed a new class of celestial objects,
forever changing our understanding of stellar evolution and the life cycles of stars.
Anthony Hewish's leadership and theoretical insights
helped shape the field of pulsar astronomy,
paving the way for countless discoveries.
And Russell Hulse and Joseph Taylor's groundbreaking work on binary pulsars
provided the first indirect evidence for the existence of gravitational waves,
confirming one of Einstein's most profound predictions,
and opening up a new window into the study of the universe. These pioneers,
along with countless other scientists and engineers,
who have dedicated their careers to unraveling the mysteries of pulsars,
have left an enduring legacy, inspiring generations of scientists,
and igniting the imaginations of people around the world.
The discovery of pulsars was a watershed moment in astronomy, but it was just the beginning.
As we have seen, these celestial timekeepers continue to surprise and amaze us, revealing new insights into the universe's most extreme environments and challenging our understanding of fundamental physics. The future of pulsar astronomy is bright, filled with the promise of new discoveries and technological advancements that will push the boundaries of our knowledge even further. The next generation of telescopes, both on Earth and in space, will be more sensitive, powerful, and capable of observing the universe across a wider range of wavelengths than ever before. The Square Kilometre Array, poised to become the world's largest radio telescope, will revolutionize our view of the radio sky, detecting faint pulsars in distant galaxies and providing unprecedented details about their properties. New space-based telescopes, such as the European Space Agency's Athena X-ray Observatory, will probe the extreme environments around neutron stars with unprecedented clarity, revealing the secrets of their magnetic fields, superfluid cores, and the exotic forms of matter that might exist within them. And pulsar timing arrays, those cosmic-scale gravitational wave detectors, are poised to make groundbreaking discoveries, listening for the faint whispers of spacetime from merging supermassive black holes billions of light years away, providing a glimpse into the early universe and the evolution of galaxies.
The study of pulsars is not merely a scientific endeavor, it is a testament to the power of human imagination.
These celestial objects, once thought to be impossible, have captured our imaginations, inspiring artists, writers, and musicians to explore the intersection of science and art.
From science fiction novels that imagine civilizations powered by pulsars,
to musical compositions that translate their rhythmic pulses into sound,
pulsars have transcended the realm of science and entered the realm of human creativity, reminding us of the beauty and wonder that lie at the heart of the universe.
The story of pulsars is a reminder that science is not a cold, sterile pursuit of facts, but rather a journey of discovery, driven by curiosity, passion, and a sense of awe at the universe's mysteries.
It is a journey that requires both rigorous observation and creative interpretation, a dance between the rational and the imaginative.
As we continue to explore the cosmos, guided by the beacons of pulsars and other celestial wonders,
we can be sure that the universe will continue to surprise us, challenge our assumptions, and inspire us to reach for a deeper understanding of our place in the grand scheme of things. The study of pulsars, like all scientific endeavors, is ultimately a search for meaning, a quest to understand our place in the universe and the nature of reality itself.
These celestial objects, born from the death throes of massive stars, remind us of the interconnectedness of all things, the cyclical nature of the cosmos, and the vastness of time and space.
We are, after all, stardust, forged in the hearts of stars that lived and died long ago, their remnants scattered across the universe, seeding new generations of stars and planets.
The atoms in our bodies, the air we breathe, the earth beneath our feet, all were once part of a star, their journeys through time and space intertwined with the cosmic dance of pulsars and other celestial wonders.
As we stand at the precipice of a new era of discovery, poised to unlock even more secrets of the universe, we are reminded of the importance of curiosity, collaboration, and a sense of wonder.
The study of pulsars, with its blend of cutting-edge technology, international cooperation, and profound implications for our understanding of the cosmos, exemplifies the best of humanity's pursuit of knowledge.
Let us continue to explore, to question, to dream, and to marvel at the universe's infinite capacity to surprise and inspire us.
For in the rhythmic pulses of pulsars, we hear not just the echoes of distant stars, but also the heartbeat of the cosmos itself, a symphony of science, imagination, and the enduring human spirit. Like, subscribe, and stay tuned for more cosmic wonders.